Okay, so we're going to take a look at how calorimetry helps us determine the change in enthalpy and how we're going to do these calculations, okay? So with calorimetry, remember the equation we're always going to use is that Q is equal to M specific heat times the change in temperature, okay? Or Q is equal to MCAT. All right, so there's our equation. And we did that lab Friday where we actually did a calorimetry lab, and we were able to say, okay, well, we can find the change in temperature. I know the mass of my solution. In this case, our specific heat for water was 4.18 joules per gram degree Celsius. So we could calculate the heat, okay, that was produced or consumed, or the heat for that particular reaction. Okay, the problem is that, so what happens if I change the amount of chemicals I use in the reaction? Okay, so what happens then? Right? Is the heat going to stay the same? You know, so let's think back what we were doing. We were dissolving sodium hydroxide. So we're going from NaOH solid to sodium hydroxide aqueous. And what we found was that the temperature of the water increased. All right? Now, if I increase the amount of sodium hydroxide that I put in, what would we think? Well, we would think our change in temperature would be greater than or higher, right? Greater or higher than it was the first time. Oxide in the same amount of water, then my temperature change would be less than. Okay? So, do we always have to go back and find the new heat every time we want to find out what's going on for that reaction, for this particular reaction? No. So what we can do is we're going to use our Q to find delta H, or our change in enthalpy. Because our units on enthalpy are in kilojoules per mole. All right, where our units on Q are just joules. So what's the difference here? Well, if I have my delta H, okay, if I calculate my delta H, I know how many moles I have, well, I can figure out what's going to happen if I change the moles of sodium hydroxide. How much heat is going to be produced, or what's that change in internal energy? Okay, so let's look at the equation that we're going to use real quick. So the equation that we're going to use is delta H is equal to negative Q over moles. Let's talk about for a second why it's negative Q. So let's go back to our sodium hydroxide example. So in sodium hydroxide, the Q was greater than 0 because heat was produced, right? Our temperature increased. So if we look mathematically at our equation here, you know, we have a positive mass, positive specific heat, and a positive delta T. So that means my Q would also be positive. Well, let's think about what's going on in the reaction. If my Q is positive, or if heat was produced, that means my reactants were at a higher energy state than my products. Okay? Because my, you know, as it went through the reaction, it went to a more stable energy state, and heat was released, or heat was produced, because energy is being conserved there. Well, if heat is being produced, my Q is going to be greater than 0. But what's my delta H here? My delta H is actually what? Negative, because I decrease. So we have negative Q over moles. All right, so let's come down here and look at an example problem. Okay, when 4.25 grams of sodium ammonium nitrate dissolves in 60 grams of water in a coffee cup calorimeter, temperature drops from 22 degrees Celsius to 16.9 degrees Celsius. Calculate the delta H of the solution process. Right? Assume the specific heat of the solution is the same at water. So we're going to use that 4.18 joules per gram degrees Celsius. All right, well, let's set this up. So they did a calorimetry problem, so we know we're going to have to use Q equals MCAT. Okay, my mass is going to be my mass of the solution. So I have 60 grams of water and 4.25 grams of the solid. So I've got 64.25 grams times the specific heat, 4.18 joules per gram degrees Celsius, times the change in temperature. So we have 22.0, sorry, final minus initial, I did that wrong. 16.9 minus 22.0 degrees Celsius. And after you plug that into the calculator, what you get is a Q of negative 1,369.6, but we really can't be that specific, so we'll do negative 1,370 joules. Okay, so here's my heat. So what does a negative heat tell me? What tells me the flow of the energy in this case, right? I'm not losing heat, but what's going on here is if you think here's your system and here's your surroundings, the heat is going from the surroundings into the system. So this is an endothermic reaction. We also know it's endothermic because the temperature dropped, right? That's a big indication. All right, so let's finish it off. Well, that was the heat that was transferred just for this example, right? 4.25 grams and 60 degrees of water, okay? So let's determine the delta H now for this process. So what reaction do we actually have going on here? We have ammonium nitrate, okay, solid, going to ammonium nitrate aqueous. Okay, so that's the process that we have going on right now. Okay. So if we want to find the delta H for that, well, we have an equation that helps us set that up. We know that delta H is equal to negative Q over moles. Okay, moles of what? In this case, it's going to be the moles of what's dissolving. So let's go ahead and do that. So we know it's 1370 joules divided by, let's find out how many moles we have. So I'm going to pause and calculate the molar mass of this real quick. Okay, so the molar mass of ammonium nitrate is 80 grams per mole, right? And in this particular problem, I had 4.25 grams, so divided by 80 grams per mole gets me a mole of 0.053 moles. Okay, so I'm going to put that there, 0.053 moles. So 1370 divided by 0.053 gets me a delta H of a positive 25,850 joules per mole. More often you see this recorded in kilojoules, so 25.8 kilojoules per mole. Right? So there's my delta H for solution for sodium or ammonium nitrate. Okay. It's a positive number, so let's think of what's going on here. So that means that my reactants down here and my products then are up here. Right? So I have to input, okay? Heat has to enter the system. So positive delta H. So this is an endothermic. Excuse me. Endothermic reaction.